Ladies and gentlemen, today we're going to talk about your connecting your Vex and RobotC and the electrical engineering responsibilities. This is what you have to do. We can't just start building, throw stuff together. There's certain procedures that we have to follow, certain things that we have to do. So let's look at being an electrical engineer. These are your responsibilities. One is you have to keep your batteries charged. Now, I know that this may be some issues because I've seen you guys, I've seen your laptops, you come in and you want to be able to plug in your laptop. Your robot does not work that way. If your battery is not charged when you start, then your robot's useless. You have to have a charged battery to start with. You can't plug in your robot and then try to use it. Second thing, we're going to work with mechanical engineers to attach the batteries, motors, sensors to the model and to the Cortex. So, this is connecting the devices to what you're building. Then work with the computer engineers to complete motor and sensor setup, and then complete the motor and sensor schematic on automation through programming summary. What this means is each of you will have your own jobs. Sometimes you may be an electrical engineer, sometimes you may be a computer engineer. It'll change back and forth. Some of you will spend most of your time doing programming. Everyone has a spot that they're going to be best at. This is the Cortex. I've shown you a couple of these in class. Okay, this is your microcontroller, which coordinates the flow of information and power on the robot. These go to all of its systems, how many motors are turning, how much power goes to each motor, whether it has bumped a switch on there. The way to think of this is the total brain for the Vex. This is where everything input and all output comes from. Now, we already mentioned keeping the batteries charged. Every robot needs to have a power source to operate it. We're going to use a 7.2 volt rechargeable battery with each of these. We do have larger batteries. For those of you in robotics, you've seen them. For the devices we're using, this is the largest battery that we're going to need. You always need to make sure that the battery's attached somewhere. We do have battery straps, but you can also build housings for your batteries or just use zip ties. But you do not want your batteries falling off and into your mechanisms that you're building. Now, another thing, once your battery is attached, you have to make sure that your cord is long enough to reach and that there's positions for it. We'll work with that when we build it. This little device, this is what will charge. You have to be very careful because on these chargers, there are two settings. Okay, there's a slow mode and a fast mode, a safe mode. Okay, your safe mode is what we're going to be using. The fast mode helps to charge the battery quickly, but if it's left on the fast mode, it can actually damage the battery, or the battery can rupture and spill whatever contents of the battery are there, different types of acids. We definitely do not want that. So most of the time we're going to be charging with safe mode. Anytime we leave a battery plugged in, it'll be plugged in the safe mode, so you can leave it overnight. Now, attaching the motors. These motors will bolt on. I know a lot of you have seen them, and these motors are going to give you rotary motion. A lot of times you can attach the motor straight to your device. Let's say you're building a car, you can attach the motor straight to the wheel. But in order to change the torque and the speed, you're going to want to add some type of gear train to it. Either a simple gear train like you see here in this picture, or maybe a chain drive that you can add later on. There are two methods that we're going to use to connect a 2-wire motor to the Cortex. Look right here. One, it says motor port 1 and 10 is where you can connect it. And motor ports 2 through 9 you have to connect using a motor controller. Okay, this motor controller right here, we will be using motor controllers on all of our motors, and all motors will be plugged in between 2 and 9. These are the positions on the Cortex when you look at the top piece. Now, connecting the end of the Vex motor controllers to the 2-wire motor, we have to make sure that you align these wires carefully. There's two little small wires that protrude from right here. I know they're hard to see. This one has 3, and there's 2 from the motor. If these are bent, then the wire does not properly plug into the Cortex, and it will not work. If you bend them back and forth a couple of times, they will break off, and it becomes completely useless. We have to rewire them at that point, so we want to be really careful plugging these in and out and unplugging them. Alright, the claw. We may not get to using the claw on much that we have, but this will give you an idea of what it looks like. So if you look right here, you'll notice that the motor on the top is used to open and close the claw. Okay. You will need to add different motors to different positions to move the claw up and down, maybe side to side. sensors. This is called a button switch, limit switch, line tracker, and potentiometer. The potentiometer is going to tell you how many degrees of rotation there are. The bump switch is going to tell you when something is bumped and then released. So this doesn't just touch and turn on and off. That's what the limit switch says. This has two settings, bumped and then released. Line trackers help you to determine where a line is. You can follow something. So if you we'll have a dark sheet of paper down and we'll put a white line or a white strip of tape through the middle, and then the white strip of tape will turn. And you're going to create a car that will follow that piece of tape and will turn according to what's there. Bumper switch. This is a digital signal. This is very important. When you see digital and analog, you need to remember those because that's the input you'll use on the computer. These are the values. 1 is pressed, 0 is released. We talked about the 1 and the 0, open, closed, on, off. The bumper sensor is a physical switch. It tells the robot whether the bumper is on the front of the sensor is being pushed in. So if you put a bumper on the front of your device, if it bumps into a wall, it tells it that it's being pushed in. So right here, SP-ST switch, single pole, single throw, configured for normally open behavior. Look at this right here. It stays open, you push it, it closes, and then when you release it, it opens again. There's all kinds of applications for this switch, anything from starting the device to telling it to back off of something or that you found an item to pick up perhaps. Limit switch. These become very important when you have something that's moving from one place to another that could break your device if it continues. This is a digital switch as well, digital signal. It has a 1 if pressed, 0 if released. The limit switch sensor is a physical switch indicating whether the arm has been pushed down. This is a SPDT micro switch configured for SP-ST normally open behavior. Look right here where it says signal behavior. It's normally open, push down, close it. Line trackers. These are a little more complicated to set up and they're a lot more complicated to program because with them you have to program a certain range. These are analog. So the range is from 0 to 4095 depending on the amount of light being reflected back into it. A line follower uses an infrared light sensor and an infrared LED. So it illuminates a surface with an infrared light and then the sensor senses the reflected radiation. So the light itself is sent out and then it reflects back. The intensity determines the surface reflectivity. Okay? Lightly colored surface will reflect more light than dark surface. The sensor detects a dark line on a pale surface or a pale line on a dark surface. What you can do is it will tell you how much light is being reflected. So if you have 3 of them and one in the middle is staying on the line and the other 2 stay dark, what happens is you write a program so that if one side all of a sudden bumps into the light side and falls below a certain range or above a certain range, it's reflecting more light, then you would tell the motor on the right side to slow down and the motor on the left side to speed up a little bit until both the sensors on the side are not reflecting light and the middle one is reflecting the most light, and then both motors go forward again. If it veers off to the right too far, same thing would happen. This sensor would say, hey, it's getting too bright over here, so we need to slow down one motor on the left side and speed up the motor on the right side. And your car is going to drive left and right, staying on those lines. Look right here, you can see the line sensors here, hooked up to, of course, your Cortex, buttons, limit switch. Line trackers. Line follower is an analog sensor, meaning that its output covers a range of values. Okay, this is what I just talked about. In this case, from 0 to 5 volts, rather than being only high 5 volts or low 0 volts in the case for a digital sensor. So digital sensor is 1, 0. This analog, look at the scale right here, maximum, minimum, for your line trackers. You can use line trackers to help the robot navigate, as I just said. You can mark the path. A typical application uses 3 line follower sensors, such as the middle sensor is over the line your robot is following. And then you can program the sides to say at which range and which color do you need to alter or change the direction that the motors are turning. Alright, line trackers as well. There's other applications. Okay, you can use line trackers to find the boundaries between two high contrast surfaces. So you can use it for distance. You can use it to tell if something's at a certain level. Okay. The optimal range for the line tracker to read a value is 1/4 of an inch. In this elevator mode, the line tracker sensor is used to determine if the elevator is at the correct floor. So as this goes down, you have 1, 2, 3 levels. Depending on where it stops, will determine which floor you're on, because the computer can sense it with the line tracker. This one, potentiometer. This is an analog signal, so it has a value range 0 to 4095. The potentiometer is used to measure the angular position of the axle or shaft passing through its center. Okay. The center of a sensor can rotate through 265 degrees, and output value ranges from 0 to 4095 within the Vex controller. So here's a caution. When mounting the potentiometer to the robot, be sure the range of the motion of the rotating shaft does not exceed that of the sensor. Failure to do so may result in damage to your robot and the potentiometer. Here's what that's saying. If you hook the potentiometer straight up to a motor that's spinning and turn it on, the potentiometer only has 265 degrees. Once you pass 265 degrees, it will actually break your potentiometer and will no longer function as it's supposed to. RobotC programming. All of you have seen RobotC. You have it on your computers. All of you have access to it. So let's talk about working on it. All of you will be creating some sort of code. Some of you more elaborate, some of you very simple, but everyone will be writing a code. Right here, if we click the robot button, we see motors and sensor setup. Under motors and sensor setup, you're going to configure and name each motor and sensor that's connected to the robot. Right here we have claw motor, right motor, left motor. Look at it as it says. It says type a name to describe the motor or location. But what do you notice about the names? Hopefully you notice that the beginning letter is lowercase. There's no space between the second word. And this letter, the first letter of the second word, is capitalized. That is for everything. This is a standard way of writing down information, a standard way of naming parts in a computer system. Now after you do that, you also have to remember the ports 1 and 10 can be used for 2-wire motors. You can also use a motor controller for 29 to plug into ports 2 through 9. So you have to tell it where you're plugging it in, and then also check the reversed if you want the motor to run in the opposite direction. Now this is a little confusing when you're writing code, because as we know, if we go into positive numbers, positive 65 will go one direction, negative 65 will go the other. But if you click the reversed button, positive will go the way that the negative was going, and negative will go the way that positive was going. So you have to make sure you know which way your motor's turning, whether or not you want the powers reversed, and what direction you're going to have the flow of power, whether it's positive or negative. Now, your analog sensors. We had mentioned a couple analog sensors. Those were the line followers and potentiometer. There are many more analog sensors and digital sensors, but these are all the ones that we're going to be using for this class. First off, you type the name to describe the sensor. Once again, lowercase l, capital F. Potentiometer is all one word, so it's just capitalized potentiometer. And then you choose the type. You have to remember to click and choose the type, otherwise you have input to labeled, but nothing that it's going out to or nothing that's being sensed with. Digital. In digital, the switches are on or off, 1 or 0. We also run the same thing right here with LEDs. LEDs are either power on or power off. They can be plugged into ports 1 through 12, and the types are listed here. Same thing with the limit switch and bump switch. Both of these are as touch sensors. Right here it says, complete the motor and sensor schematic on automation through programming summary. This right here will allow you to create your own schematic, writing down what's in which port, which digital pieces here, which analog pieces plugged into here, so that when you look at your robot, you know exactly what wires go where. That is the end of the slide for now. I'm not going to make you complete this until after we've gotten to work with the work with the materials, decide what's going on, and build our test bed. Thanks, and I hope you have a good evening.